So it turns out there's a massive tectonic ticking time bomb lurking just off the west coast of North America. And it's not just some doomsday sci-fi theory. It's a very real geological system that's been studied for decades but still isn't fully understood. This region is home to one of the most dangerous fault lines on Earth, and experts have been warning that a megaquake here isn't just possible, it's inevitable. The only uncertainty is when. The focus of this concern is the Cascadia subduction zone, a terrifyingly long fault that stretches from northern California all the way up past Vancouver Island. We're talking about a fault line that runs for nearly 700 miles beneath the ocean. And unlike the San Andreas Fault, which most people have at least heard of, Cascadia is quiet. Too quiet. That's what makes it so unnerving. While the San Andreas tends to relieve pressure through frequent smaller quakes, Cascadia has been locked, storing up colossal amounts of energy for centuries. Here's where things get spooky. The last time Cascadia unleashed its full fury was on January 26, 1700. That date is oddly specific considering there were no written records in the Pacific Northwest at the time. But we know it happened because the quake was so massive, estimated at magnitude 9.0 or higher, that it sent a tsunami surging across the Pacific Ocean and slammed into the coast of Japan. Japanese officials had documented the so-called orphan tsunami that appeared without warning. They didn't know where it came from, but now, thanks to centuries of geologic detective work, we do. Researchers pieced it together through oral traditions of indigenous tribes, drowned forests along the Pacific Northwest, layers of sand deposited miles inland, and Japanese tsunami logs. It's like a forensic investigation into the Earth's deep past. And what they found is that this wasn't a one-off event. The Cascadia subduction zone has a violent history of generating megaquakes every 300 to 600 years. You don't need a calculator to realize we're already deep into the danger window. But here's the truly chilling part. This fault doesn't release energy in small, manageable doses. Instead, it builds and builds until one day, without warning, it snaps. And when it does, the result could be one of the deadliest natural disasters in US history. We're not talking about a typical earthquake that rattles the dishes and knocks some pictures off the wall. We're talking about entire regions being torn apart, coastlines dropping by several feet, and a wall of water racing inland, swallowing entire towns in minutes. If that sounds like fear-mongering, think again. FEMA, the Federal Emergency Management Agency, has modeled what a full rupture of the Cascadia subduction zone might look like. According to their simulations, a magnitude 9.0 earthquake followed by a tsunami reaching over 100 feet tall could devastate the coasts of Oregon, Washington, and Northern California. Thousands of buildings would collapse. Bridges would crumble. Roads would be shredded like paper. And depending on the time of day, the death toll could reach into the tens of thousands, possibly more. Cities like Seattle, Portland, and Eugene would be rocked for minutes. Not seconds. Minutes. That kind of sustained shaking would be unlike anything most people have ever experienced. Emergency services would be overwhelmed. Power grids could fail. Cellular networks would be knocked out. It could take weeks, maybe months, to reach some communities cut off by landslides, broken highways, and collapsed infrastructure. And then there's the tsunami. Within minutes of the quake, a massive wave would begin forming offshore. Unlike tsunamis caused by underwater landslides or volcanic eruptions, which are more localized, a subduction zone rupture lifts an entire slab of the seafloor, displacing a mind-boggling volume of water. That displaced water turns into a surge traveling hundreds of miles per hour. Along the coastline, residents would have perhaps 10 to 15 minutes, if they're lucky, to get to high ground. Sirens might not work. Roads might be jammed or impassable. And in many coastal towns, there simply isn't enough elevation to escape to. Now imagine the sheer scale of the disaster. Hospitals could be reduced to rubble. Airports rendered unusable. Ports destroyed. Emergency responders trapped. Supply lines severed. You'd have tens of thousands of survivors in desperate need of food, water, and shelter, and not nearly enough resources to go around. It's easy to assume this kind of scenario is just theoretical. But here's where it gets even more unsettling. In 2011, Japan experienced something very similar. The Tohoku earthquake, which measured 9.1, also occurred along the subduction zone. It unleashed a tsunami that killed over 20,000 people, caused the Fukushima nuclear disaster, and inflicted economic damage totaling hundreds of billions of dollars. And yet the Tohoku fault was considered less dangerous than Cascadia. Think about that for a second. In fact, Japanese scientists were caught off guard by how big that quake got. Their models had underestimated the potential size. The parallels to Cascadia are hard to ignore. US researchers are now openly acknowledging that we might also be underestimating the scale of what's coming. Seismologists have been deploying more sensors along the Pacific Northwest coast, drilling into sediments to study the earthquake history, and running sophisticated simulations of rupture scenarios. What they're finding is deeply concerning. The entire fault could rupture in one go, or in segments. But if it goes all at once, the energy release would be on par with the largest earthquakes ever recorded in human history. Even the soil in parts of the Pacific Northwest is a silent accomplice in this looming disaster. The region is full of soft, waterlogged ground, especially around river deltas and coastal plains. When the shaking starts, this ground can liquefy, turning into something like quicksand. Buildings that once stood tall can suddenly tilt, sink, or collapse outright. This phenomenon was seen during the 1989 Loma Prieta earthquake and again during Japan's 2011 disaster, where entire city blocks tilted like broken dominoes. And then there's another issue: the infrastructure. Much of the Pacific Northwest's critical infrastructure was built without a full understanding of the Cascadia threat. Bridges, schools, and hospitals weren't constructed to withstand a 9.0 quake. Some retrofits have been done, yes, but many vulnerable structures remain. A 2015 report by the Oregon Seismic Safety Policy Advisory Commission even stated that over 1 million buildings in Oregon alone could be unsafe during a Cascadia megaquake. So now the question becomes, are we ready? And the honest answer is, probably not. Emergency planners are trying. There are evacuation drills, tsunami escape routes, and public awareness campaigns. But the scale of the threat is so enormous, it's difficult to fully prepare. Most people don't want to think about it. It's uncomfortable. But ignoring it doesn't make it any less real. And here's something even more mind-bending. Some scientists are beginning to suspect that the Cascadia subduction zone may already be showing signs of stress, subtle hints that it could be gearing up for something big. Small tremor events, known as episodic tremor and slip, have been detected deep in the earth along this fault line. These aren't full-blown earthquakes. They're more like ghost quakes, slow, silent shifts that occur over days or weeks. And while they don't cause damage, they do indicate that pressure is building. Nobody knows if these tremors are precursors or just part of a natural cycle. But some researchers believe they might be the Earth's way of warning us, whispers from the crust that something enormous is stirring below. Beneath the western edge of North America, something ancient and relentless is unfolding, a slow-motion confrontation between massive slabs of Earth's crust. These tectonic plates are colossal beyond imagination, stretching for thousands of miles and weighing billions of tons, yet they are in constant, almost imperceptible motion. Along the boundary where the Pacific Plate meets the North American Plate, the stress has been quietly mounting for centuries. It's not the kind of drama we notice in daily life. To the casual observer, the land appears still, calm, and unchanged. But in the deep silence beneath the ground, forces are twisting and grinding against one another, storing tension like a drawn bow, waiting for the moment it snaps. This tectonic tug-of-war is not a distant scientific abstraction. It's a slow-building crisis with the power to reshape entire regions in an instant. One of the most studied and feared fault lines in the United States is the San Andreas Fault, a name that has become synonymous with earthquake risk. This massive fracture in the Earth's crust stretches roughly 800 miles through California, carving its way through valleys, deserts, and even cityscapes. But the fault is not a single, clean crack. It's an intricate system of interconnected fractures, each with its own personality and potential for disruption. Of particular concern to geologists is the southern portion of the San Andreas, which runs near the Salton Sea. This segment hasn't ruptured in more than 3 centuries. That's significant, because historical data suggests it typically releases its built-up stress every 150 to 200 years. The longer it stays silent, the more pressure accumulates, pressure that will one day demand release. When that release comes, experts fear it could trigger a magnitude 7.8 or even larger earthquake. Such a quake wouldn't just jolt the Earth, it would tear across the landscape with staggering force. To put it in perspective, a quake of that size would unleash energy equivalent to hundreds of Hiroshima-sized atomic bombs detonating simultaneously underground. The shaking would ripple through the ground like waves in water, radiating outward from the epicenter and affecting an enormous area. Cities like Los Angeles, San Bernardino, Palm Springs, and Riverside could be hit hard. Even communities many miles from the fault line could feel the shock, depending on the depth and intensity of the rupture. And unlike deep focus earthquakes, which lose energy before reaching the surface, this type of event would be shallow and close to densely populated zones, making the potential for devastation even greater. Modern California is a marvel of engineering and human achievement, but it is also incredibly vulnerable. Highways, bridges, power lines, and skyscrapers crisscross the landscape in every direction. While updated building codes and emergency planning have made strides, experts are concerned that the scale of a major San Andreas rupture would still overwhelm existing systems. Picture this: freeways collapsing mid-commute, communication lines cut in an instant, emergency responders scrambling through debris-choked streets, and millions suddenly thrust into chaos. In older neighborhoods, or poorly retrofitted buildings, entire structures could crumble. The economy of the entire West Coast, and perhaps the nation, could take a serious hit. And in the aftermath, it wouldn't just be physical structures needing repair. There would be emotional and psychological fallout too. People who survive such quakes often describe the sound as a deep, unearthly roar, followed by the gut-wrenching sensation of the earth itself coming alive beneath their feet. History offers us chilling clues about what such an event might look like. The Great San Francisco earthquake of 1906 was a catastrophic example of what the San Andreas Fault is capable of. Measuring an estimated magnitude 7.9, it destroyed more than 80% of the city and left over 250,000 people homeless. But that was over a century ago, when California's population and infrastructure were a fraction of what they are today. If a similar event struck now, the losses could be exponentially greater. And even more concerning is the fact that while much attention is focused on the San Andreas, it's not the only seismic threat lurking beneath the western United States. Further north, stretching from northern California up through the coasts of Oregon and Washington, lies a hidden danger that dwarfs even the San Andreas in destructive potential: the Cascadia subduction zone. This massive fault is the boundary where the oceanic Juan de Fuca plate dives beneath the North American plate. Unlike the San Andreas, which slides laterally, the Cascadia subduction zone operates as a megathrust fault, and that difference matters. Megathrust earthquakes are among the most powerful natural events on Earth. In the right conditions, Cascadia is capable of producing a magnitude 9.0 earthquake, or higher. To understand what that means, consider that a 9.0 quake would not only flatten buildings and twist highways but could also displace entire sections of coastline, permanently altering the geography. The last time Cascadia ruptured was in the year 1700, long before the West Coast was settled by modern civilization. But we know it happened because the evidence is everywhere. Japanese records from that time describe a mysterious tsunami hitting their shores without any accompanying earthquake, a phenomenon now linked to the Cascadia event across the Pacific. In North America, scientists have found ghost forests, stands of trees that were instantly killed when the land suddenly sank and salt water rushed in. Core samples pulled from coastal marshes show layers of sand pushed inland by massive waves. All of this points to a full margin rupture in Cascadia over 300 years ago, and the geological clock suggests we are now entering the window for its next cycle. When, not if, this fault ruptures again, the Pacific Northwest could be hit with both a massive quake and a wall of water within minutes. To truly grasp the threat Cascadia poses, it's important to understand the way it operates in silence. Unlike the San Andreas Fault, which produces more frequent smaller quakes, Cascadia is ominously quiet. It doesn't tremble often, and that silence is misleading. In geological terms, quiet isn't calm, it's restrained. Scientists refer to this kind of fault as locked, meaning the plates are stuck against each other, unable to slide past smoothly. Over centuries, strain accumulates, and when the energy finally overcomes the friction holding the plates together, it is released all at once. This sudden slip can rupture hundreds of miles of fault line in a single event, sending seismic shockwaves across multiple states and into Canada. What makes this even more dangerous is how long it's been since the last rupture. The longer a subduction zone stays locked, the more energy it stores, and the more catastrophic the release. Researchers at universities like Oregon State and the University of Washington have used cutting-edge modeling, deep-sea sediment analysis, and GPS data to better understand the behavior of Cascadia. They've discovered that the fault is segmented into northern, central, and southern portions, each capable of rupturing independently. But when the entire margin breaks at once, the consequences become apocalyptic. A full margin rupture, spanning roughly 700 miles, could unleash shaking that lasts 5 minutes or longer. That kind of sustained ground motion is profoundly destabilizing. It's not just a sharp jolt and done, it's a prolonged, violent rocking that wears down structures, disrupts infrastructure, and overwhelms the human nervous system. The psychological impact of long-duration shaking is a lesser-known but very real hazard. People struggle to stay upright, emergency response systems falter under prolonged duress, and panic can quickly overtake order. One of the most unsettling aspects of a major Cascadia event is the immediate double threat it presents. Within moments of the initial seismic rupture, the displacement of the seafloor would generate a massive tsunami. This wave wouldn't creep in slowly. It would travel at jetliner speeds, racing across the Pacific and slamming into the west coast with little time for warning. Coastal towns like Seaside, Oregon, Crescent City, California, and Long Beach, Washington lie within the tsunami inundation zones. In these areas, evacuation windows are desperately short, sometimes as little as 10 to 15 minutes. Unlike more gradual flood events, this wave would arrive as a wall of water, sweeping inland and leveling everything in its path. Entire neighborhoods, schools, hospitals, and businesses could be washed away before residents have a chance to escape. Even areas thought to be outside the primary danger zone could experience severe flooding due to the force and height of the wave. What compounds the concern is that large portions of the Pacific Northwest were not built with this level of risk in mind. In fact, the scientific recognition of the Cascadia subduction zone as a megaquake threat is relatively recent, becoming widely understood only in the late 20th century. That means cities like Portland, Seattle, and Eugene have significant infrastructure that predates modern seismic codes. Many bridges, overpasses, and high-rise buildings were constructed under the assumption that the region was low risk for massive quakes. Hospitals, fire stations, and schools may be especially vulnerable. In addition, unlike earthquake-hardened areas like Southern California, the Pacific Northwest has far fewer retrofitted buildings. This creates a landscape of quiet fragility, urban and rural zones alike poised on the edge of a disaster they were never truly prepared for. Emergency planners are painfully aware of these vulnerabilities. FEMA has developed scenarios like the Cascadia Rising Drill, simulating a full margin rupture and its aftermath. The results of these exercises are sobering. Roads become impassable. Airports are damaged or submerged. Cell towers topple. Electricity goes dark for weeks. Clean water becomes scarce. Supply chains grind to a halt. Even with preparation, experts estimate tens of thousands of fatalities and millions of displaced residents in the worst-case scenario. And the emergency response would be hampered not only by damaged infrastructure, but also by sheer geographic isolation, many coastal towns are connected by a single road in or out. If that route is destroyed, help may not arrive for days. But beyond the sheer physical destruction, there's another layer to consider: the lingering environmental aftermath. A rupture of this magnitude would disturb not only the human-built world but also the natural one. Forests could collapse due to landslides triggered by intense shaking. River paths might shift. Estuaries and wetlands could be choked with debris. Even the ocean itself would be transformed, as massive underwater landslides could occur along the continental slope, further exacerbating tsunami risk. The ecological scars of such an event would last for generations. Entire species could be affected by the disruption of coastal habitats. And with potential nuclear facilities, chemical plants, and sewage treatment stations located within impact zones, secondary contamination could lead to long-term consequences for both wildlife and human populations. Moving on to tectonic research, particularly in subduction zones like Cascadia, it has evolved drastically over the past few decades. What was once a vague and largely theoretical field has transformed into a precise, data-driven science thanks to the rapid advancement of technology. Today, researchers are able to observe the movements of tectonic plates in real time with astonishing accuracy. This is largely due to dense networks of GPS monitoring stations placed strategically across the Pacific Northwest. These stations, no larger than a backpack, are anchored into the ground and communicate with satellites to detect even the most minute shifts in the Earth's surface, sometimes as small as a few millimeters per year. Over time, these tiny shifts accumulate and paint a picture of where strain is building, and more importantly, where it's most likely to be released. One of the more groundbreaking aspects of tectonic research is the use of seafloor pressure sensors and ocean bottom seismometers. Since a large portion of the Cascadia subduction zone lies offshore, these instruments are vital. Installed directly on the ocean floor, they continuously measure the vertical motion of the crust and track pressure changes that may indicate plate movement. By deploying ships and remotely operated vehicles, scientists have successfully positioned these sensors in some of the most remote and geologically active parts of the seafloor. What they're finding is that stress is not evenly distributed. Certain segments of the fault are showing more resistance than others. This patchwork of stress accumulation is critical to understanding which portions might rupture next, and whether they will fail independently or cascade into a full margin event. Another key method used in tectonic research is paleoseismology, the study of past earthquakes through geological evidence. This involves digging trenches along faults, examining layers of sediment, and identifying disruptions that correspond with historical or prehistoric seismic events. Along the coastlines of Oregon and Washington, researchers have uncovered layers of sand deposited by ancient tsunamis, interbedded with soil layers and buried vegetation. These geological fingerprints offer a timeline of Cascadia's seismic history. For example, one of the most conclusive discoveries was the correlation between a massive quake in the Pacific Northwest and a documented tsunami that struck Japan in the year 1700. Japanese records spoke of an orphan tsunami, one that arrived without a local earthquake, mystifying at the time. But sediment evidence from North America later proved that the tsunami originated from a colossal rupture in the Cascadia subduction zone, connecting two continents through the legacy of destruction. In addition to physical records, tectonic research increasingly relies on modeling and simulation. Supercomputers now run complex algorithms simulating how different fault segments might behave under stress. These models incorporate real-world data, including rock composition, fault geometry, and historical rupture patterns. By running millions of hypothetical scenarios, researchers can estimate the probability of various outcomes, from a partial rupture affecting only southern Oregon to a full-scale event stretching from California to British Columbia. These simulations don't offer exact predictions, but they do help emergency planners and policymakers understand the most likely and most dangerous possibilities. An especially fascinating breakthrough in recent years has been the identification of slow slip events, or silent earthquakes. These are tectonic shifts that occur over days or weeks rather than seconds. While they don't cause surface shaking, they still represent a release of tectonic stress and can sometimes precede or follow larger quakes. Cascadia is known to experience these silent slips, particularly in the deeper parts of the fault. Instruments have detected these subtle movements approximately every 14 months in certain regions. What's intriguing is that these slow slip events might be acting as pressure valves, briefly easing the strain building along lock segments. Or, alternatively, they may act as warning signals, indicating that stress is migrating toward a critical point. Scientists are still debating their true significance, but one thing is clear: they represent a crucial piece of the tectonic puzzle. On the frontier of tectonic research, geophysicists are also experimenting with acoustic emissions and strain meters embedded deep within boreholes. These devices, some installed over 2 miles below the surface, can detect the tiniest fractures or acoustic anomalies in rock layers before a fault ruptures. By listening to the Earth in this way, researchers hope to develop early warning systems, not unlike how meteorologists use radar to track storms. Although earthquake prediction remains elusive, the growing body of data suggests that certain precursory signals might eventually become reliable indicators of an impending quake. While much of the scientific community keeps its gaze fixed on major fault lines like Cascadia or San Andreas, there are deeper, less obvious drivers of seismic activity that may be equally as catastrophic, hidden mechanisms buried deep within the Earth's mantle, where the forces are far greater than anything we experience on the surface. One of the most quietly alarming of these processes is slab rollback, a phenomenon that has slowly begun to garner attention for its potential to trigger massive, unpredictable megaquakes. Slab rollback occurs when a tectonic plate, which is in the process of subducting, sliding beneath another plate, begins to pull back, retreating into the mantle like a slow-motion collapse of a massive underground trapdoor. Imagine a plate that has been sinking slowly over millions of years. The sheer force of this subduction causes a kind of stretching of the overlying crust. This stretching weakens the Earth's outer shell and, in some cases, can create conditions where faults are pushed to the edge of failure. While the process itself happens miles beneath our feet, the impact it causes can be far-reaching, potentially resulting in catastrophic earthquakes that may not align with traditional seismic activity from well-known fault lines. In areas where slab rollback is taking place, such as regions in the western Pacific or along parts of inland fault systems, the deformation it creates in the upper layers of the Earth's crust can often lead to the activation or the creation of new, previously unrecognized fault zones. These faults can then produce significant seismic events. The danger with this is that these quakes may strike unexpectedly, in regions where people do not expect a major earthquake to occur. They are less likely to have built infrastructure that can withstand such an event, and emergency preparedness is often insufficient. This makes rollback-induced quakes especially terrifying. They emerge from places that are not typically associated with seismic danger, catching people off guard, as these areas may not have been subjected to regular seismic monitoring or the same level of hazard assessment. But rollback is just one part of the puzzle. Another increasingly discussed phenomenon in the field of seismology involves deep-focus earthquakes, which occur much deeper in the Earth's crust than the typical shallow quakes we are used to hearing about. Deep-focus earthquakes happen at depths of 300 kilometers or more beneath the surface, where the pressure and temperature are so high that they change the behavior of the rocks and minerals involved. While deep-focus earthquakes are generally smaller in magnitude compared to shallow ones, they have the potential to trigger seismic activity in faults much closer to the surface. The energy released deep within the Earth's crust can travel upward, sometimes causing a cascading effect that might push nearby faults to rupture. This is especially concerning because deep earthquakes are far harder to predict, and we lack a full understanding of how their energy might transfer to other fault systems. There are mounting studies, particularly in regions like Japan and South America, where the occurrence of deep-focus earthquakes has often been followed by major quakes closer to the surface. This could suggest that deep seismic activity might be more connected to surface-level events than we once thought. While scientists are still piecing together the full dynamics, the possibility remains that these deep quakes could set off catastrophic events in areas we might not traditionally associate with such danger. It's as if the earthquakes from deep within the Earth's crust are priming the faults nearer the surface, making them more susceptible to rupture under the right conditions. The alarming potential of these deep focus earthquakes is that they can occur without any clear indications that a larger, more destructive quake is imminent, catching both scientists and the public by surprise. Alongside these seismic forces, there's another factor that is slowly being recognized for its role in the potential for megaquakes: glacial isostatic rebound. This may sound somewhat distant and obscure, but the reality is that it's something happening right now, though most of us have no idea. During the last ice age, enormous ice sheets covered much of the northern parts of the globe, from Canada to Scandinavia. As these ice sheets slowly melted over the past several thousand years, they released the pressure that had been pushing down on the Earth's crust. However, the land that was once compressed by the ice is still slowly rising in a process known as isostatic rebound. This adjustment is so gradual that it's nearly imperceptible on a human timescale, but it's a massive force of nature unfolding beneath our feet. What makes glacial rebound so concerning is that it can destabilize regions where this process is occurring. The weight of the ice may have kept faults compressed, but as the land slowly rises, it could redistribute the stress within the Earth's crust, causing previously stable zones to become prone to faulting. As the land adjusts, it can cause weak points to form in the crust, creating the potential for an earthquake to occur. This process is not confined to any one specific area but is taking place in regions like northern Canada, parts of Alaska, and Scandinavia, and scientists are beginning to monitor these areas more closely. While these quakes may not be huge on their own, the accumulated stress could reach a tipping point, triggering massive earthquakes along existing fault systems. In particular, areas of North America, such as Alaska and even parts of the Pacific Northwest, are under increasing observation for this very reason. The ongoing land uplift from glacial rebound could lead to the formation of new fault zones, especially in places where other seismic factors are already in play. If enough stress builds up, it could be just the catalyst needed for a catastrophic event, especially if the fault systems involved are near a critical point of instability. What makes glacial isostatic rebound even more unsettling is the fact that we may not fully understand the extent of the danger until it's too late. By the time scientists detect a shift in stress levels, the damage may already be done. Lastly, there's another potential cause of megaquakes that has been gaining attention over the past few decades, and that is fluid migration within the Earth's crust. Beneath our feet, deep within the Earth's layers, fluids like water and gas are constantly moving through porous rock formations, traveling along fault lines and fractures. While this movement is typically slow, the pressure exerted by fluids can lubricate faults, decreasing the friction that holds them in place. In some cases, this process can cause faults to slip unexpectedly. The movement of fluids through the crust can sometimes be triggered by human activities, such as deep water drilling, geothermal energy extraction, or even fracking, all of which introduce additional fluids into the Earth's subsurface. In regions where there are pre-existing fault zones, this can add additional pressure to already unstable areas. While the connection between human activities and induced seismicity is well established for smaller earthquakes, there is growing concern that these same forces could trigger larger, more catastrophic seismic events if they interact with critically stressed fault zones. A poorly managed industrial operation in the wrong location could inadvertently push a fault system past its breaking point, leading to a major earthquake. The problem lies in the fact that this process is hard to predict, as it depends on a variety of factors: fluid pressure, the specific geology of the region, and the stress levels in the surrounding rock. But if the conditions are right, a relatively minor human action could trigger a catastrophic chain reaction that leads to a megaquake. This complex interaction of natural forces, like fluid migration, combined with human-induced stress on the crust, means that megaquakes can occur in places and ways that scientists have only just begun to understand. And because these forces are so varied and can occur in many different regions, predicting exactly when or where the next megaquake will strike remains an ongoing challenge for scientists. The Earth beneath us is a constantly shifting and evolving landscape, and while we continue to make strides in understanding its behavior, the full scope of these potential triggers remains largely a mystery. As we've seen, the causes behind a megaquake aren't always immediately visible or understood, but they are incredibly powerful forces lurking beneath the Earth's surface. Now, we'll turn our attention to the aftermath of a major seismic event. What happens after the quake strikes? It's not just the shaking that has a lasting impact. It's the destruction, the aftermath, and the long-term consequences that leave deep scars on the affected regions. When we talk about the post-disaster impact of a megaquake, we must understand that it's more than just the destruction of buildings or roads. The true toll is felt in the disruption of lives, economies, and ecosystems. In the immediate aftermath of a catastrophic quake, rescue and recovery efforts become the highest priority. But the logistical challenges of reaching those in need are immense. When a megaquake strikes, roads, bridges, and communication networks are often destroyed. First responders are faced with broken infrastructure, blocking access to affected areas. In densely populated urban centers, it may take days or even weeks before rescue teams can fully reach the most devastated regions. Meanwhile, survivors are left in precarious conditions, unable to receive the care or supplies they desperately need. The clock is ticking, and each passing hour makes the difference between life and death. Hospitals, already overwhelmed with the injured, often face shortages of medical supplies, trained staff, and equipment. But it's not just about physical aid. Mental health becomes a silent yet critical aspect of recovery. The emotional trauma from witnessing the destruction, losing loved ones, or being displaced for months or even years takes its toll on survivors. Psychological recovery often goes overlooked in the initial stages, but studies have shown that the emotional scars of experiencing a megaquake can linger for years. People who have endured a major seismic event are at a higher risk for post-traumatic stress disorder, PTSD, anxiety, depression, and other mental health issues. It's not just about rebuilding homes and infrastructure, but also rebuilding communities, minds, and spirits. Economically, the impact of a megaquake can be devastating, often pushing already vulnerable regions into deeper instability. After the immediate emergency response, the slow and painful process of reconstruction begins. This is where the true cost of the disaster starts to show. In cities where megaquakes occur, the cost of repairing or rebuilding entire neighborhoods, hospitals, schools, and businesses is astronomical. Insurance claims skyrocket, with many businesses losing years' worth of work in a matter of minutes. The strain on local economies is immense, and it can take decades to fully recover from the financial blow dealt by the earthquake. But the economic impact doesn't just end with the destruction of physical property. The disruption of local industries often leads to widespread unemployment. When factories, ports, and commercial centers are destroyed, entire workforces are left without jobs. Local businesses may be forced to shut down permanently due to the devastation, and the region's economic engine grinds to a halt. In the aftermath of a major quake, it can take years before industries resume full production, and until then, the region must rely heavily on outside aid and investment to keep things moving. For smaller towns and cities, the impact is particularly devastating. Without the financial infrastructure to weather such a storm, entire communities can be lost forever. Another side effect of a megaquake is its impact on global supply chains. It's easy to forget how interconnected the world is, but when a major earthquake disrupts a crucial trade hub, the ripples are felt worldwide. Ports, roads, and railways are often key components of the global economy, and when they're damaged or destroyed, goods and services stop flowing. For example, consider how the destruction of a major port city like Tokyo or Los Angeles could halt the shipment of everything from electronics to agricultural goods, impacting industries across continents. Companies around the world would feel the pressure, dealing with shortages and delayed deliveries, while some products may become prohibitively expensive due to the disruption in supply. Beyond the immediate and economic impacts, megaquakes also wreak havoc on the environment. When the Earth shakes violently, entire ecosystems can be disrupted. Landslides triggered by seismic activity can block rivers and waterways, leading to flooding or the loss of freshwater sources. Coastal areas may be flooded by a tsunami, erasing entire wetlands, beaches, and even wildlife habitats in an instant. It's not just human communities that suffer. Wildlife, too, is deeply affected by the destruction of their natural habitats. Earthquakes can trigger the collapse of entire forests, rivers, and coastal zones, pushing vulnerable species toward extinction. It can take decades, even centuries, for ecosystems to begin to heal after such profound disruption. But there's another aspect of a megaquake's post-disaster impact that's often overlooked: the psychological toll on entire populations. Survivors of the quake might find it hard to return to what was once considered normal. In cities where massive destruction occurs, the fear of aftershocks can linger long after the main event. There's an underlying anxiety that hangs over the population, knowing that the next big quake could happen at any moment. For many, it's not just the destruction of property or the loss of life that haunts them, it's the mental and emotional toll that stays with them in the aftermath. Families may be displaced for years, with some never being able to return to their homes. And even if they rebuild, their communities may never feel the same again. The long-term effects of this trauma can shape the way a society evolves. After a megaquake, there's often a shift in how people view their world and the stability of their environments. Trust in governmental agencies and emergency response teams can be strained, especially if there were significant delays in relief efforts or if resources were poorly managed. People may lose faith in the systems meant to protect them, which can lead to social unrest and further complications in the recovery process. In regions that are still reeling from the effects of a major quake, political instability can arise as people demand more accountability from those in power. The combined physical, emotional, economic, and environmental impacts make post-disaster recovery a monumental task, one that takes decades in some cases. But this is not the end of the story. As we've seen in countries like Japan, Chile, and Haiti, communities and countries can rebuild even after the worst events. While recovery may be slow, it's important to remember that human resilience is one of the most powerful forces in the aftermath of disaster. As we shift from immediate recovery efforts, we need to address the ongoing recovery challenges that many megaquake survivors face. While it's easy to assume that once the rubble is cleared and buildings are reconstructed, everything returns to normal, the reality is far more complex. Long-term recovery doesn't just involve rebuilding infrastructure, it's about rebuilding lives. Entire communities can be torn apart, not just physically, but emotionally, socially, and economically. One major challenge survivors often face is housing displacement. For many, their homes were destroyed or rendered uninhabitable, leaving them to live in temporary shelters for extended periods of time. It can take years for new homes to be built and fully restored, leaving families to navigate a world where stability is elusive. Imagine having your entire world upended in a moment: your home, your possessions, your sense of security. The trauma of this disruption lingers long after the dust settles. Survivors often struggle with the uncertainty of whether they'll ever be able to return to their neighborhoods or rebuild the life they once had. Cultural heritage is another often overlooked casualty in the wake of a megaquake. When historic buildings, monuments, or cultural sites are destroyed, it's not just the physical loss that's felt, but a deeper loss of identity. Communities can lose their sense of place, the landmarks that defined them, and the cultural symbols that tied generations together. For many, these sites aren't just buildings. They are part of their shared history and collective memory. When they're gone, the emotional and cultural void they leave behind can be immense. The economic ripple effects of a megaquake are felt for years, if not decades. While rebuilding efforts inject much-needed funds into the economy, the initial financial blow can be catastrophic. Cities and towns that once thrived now face a long road to recovery. Jobs are lost, businesses shutter, and entire industries must rebuild from the ground up. For the workers who depend on those industries, the wait for economic recovery is often agonizingly slow. Families who were once self-sufficient may find themselves relying on aid or moving to new regions in search of work. The impact on local economies is felt on every level, from the smallest mom-and-pop stores to multinational corporations whose supply chains are disrupted. Beyond the economy, there's the social fabric of a community to consider. Megaquakes can cause mass migration as people seek safety and stability elsewhere. Families and communities that once thrived together may find themselves scattered, making it more difficult to rebuild the social cohesion needed for a successful recovery. The loss of community connections can make it harder for individuals to heal. Support systems, often critical in times of crisis, may be weakened, leaving survivors to cope with the aftermath on their own. Let's not forget the environmental consequences that are often a lasting part of the post-quake landscape. Soil erosion can become a major issue after massive shaking disrupts the land, leaving it vulnerable to landslides and flooding. Entire landscapes can be reshaped in an instant, as mountainsides are destabilized, rivers are redirected, and coastal areas are flooded. As communities rebuild, they may have to confront these environmental challenges head-on. Farmland that was once fertile may now be unusable, and roads or infrastructure that were once in place may need to be completely redesigned to adapt to the new landscape. The environmental recovery process, like human recovery, is slow and difficult, with impacts lasting for generations. It's also important to talk about the role of technology in the recovery process. In recent years, technology has played a crucial part in disaster recovery efforts. Satellite imaging, drones, and AI-powered mapping systems are helping to assess damage more efficiently and prioritize rescue missions. Technology also aids in rebuilding efforts, as cities use advanced software and engineering techniques to design more resilient structures. Even within communities, tech-driven solutions are helping with the restoration of essential services like water, electricity, and communications. However, access to technology isn't always equal. Disparities in resources can make it harder for some regions to recover as quickly as others. In some areas, technology may be a lifeline, while in others, it may remain out of reach. Government response is another critical factor in how quickly a region can recover. After a megaquake, the role of local, regional, and national governments becomes crucial. In some cases, governments are quick to act, providing resources, personnel, and funding to support recovery. In other cases, government responses are delayed or inefficient, leaving survivors to fend for themselves in the face of overwhelming challenges. Corruption, poor planning, or insufficient infrastructure can exacerbate the situation, prolonging recovery and leaving communities even more vulnerable to future disasters. As we've seen in past earthquakes, the speed and effectiveness of the government's response can determine whether a region bounces back quickly or languishes in a prolonged crisis. Finally, we must acknowledge the role of global cooperation in the recovery process. After a megaquake, countries and international organizations often step in to offer support. From financial aid to humanitarian relief, the world rallies around the affected region to provide help. But even with this support, recovery is never immediate. International assistance, while essential, can only do so much in the face of the enormous challenges posed by a megaquake. It takes years for a region to recover fully, and often, external aid dwindles before recovery is complete, leaving local governments and communities to pick up the pieces. As the years go on, the rebuilding process continues, and while the scars of the disaster may remain, communities begin to adapt and rebuild. New technologies, improved infrastructure, and lessons learned from the past may make the area stronger and more resilient, though the emotional scars may never fully fade. As we've explored the devastating consequences of a megaquake, one thing becomes clear: early detection and warning systems have the potential to save lives. The technology to detect seismic activity before the shaking hits is advancing rapidly, yet many regions that lie on fault lines remain unprepared for the catastrophic effects of a major earthquake. Imagine a system that can detect the early signs of a quake, providing a few crucial seconds or even minutes of warning before the ground shakes violently. In those moments, it's possible to make life-saving decisions, evacuating buildings, halting trains, or shutting down critical infrastructure like gas lines to prevent fires. The concept of seismic early warning systems is not new, but it's only in recent years that their effectiveness has been realized on a larger scale. These systems work by detecting the initial, less damaging seismic waves, known as P waves, that travel faster than the more destructive S waves. By analyzing these initial signals, it's possible to estimate the size, location, and potential impact of the earthquake before the strongest shaking begins. For areas like California, Japan, and Mexico, seismic networks are already in place, helping to provide warnings, though not all regions around the world have such systems in place yet. The potential benefits of these systems are enormous. In countries like Japan, which has one of the most sophisticated early warning systems in the world, public alerts can be sent out in a matter of seconds after the initial tremors are detected. People in high-risk areas can receive notifications on their phones, television, or even through sirens, giving them time to seek shelter. These early warnings can also help to protect vital infrastructure. Automated systems can trigger the shutdown of critical services, such as cutting off power grids or stopping trains, which could help to prevent secondary disasters like fires or collisions. But while the technology has proven to be effective in some areas, global adoption remains inconsistent. In many developing countries, the costs of installing and maintaining seismic networks are prohibitive. Even in regions where systems are in place, the coverage may be incomplete or unreliable, especially in remote or rural areas. For instance, regions within the Pacific Northwest, including parts of the Cascadia subduction zone, remain largely vulnerable due to the lack of a comprehensive early warning system. This leaves entire populations exposed to the deadly effects of a megaquake with little or no warning. Seismic early warning systems also face challenges when it comes to false alarms. These systems are highly sensitive, and even a minor tremor could trigger a warning. This can lead to alert fatigue, where people become desensitized to warnings and might ignore them when a truly devastating quake strikes. Additionally, with such a complex system, there's always a risk that the warning may be too short or too inaccurate to be useful. The timing, precision, and scope of these alerts are all factors that continue to be improved, but they still present challenges. Despite these obstacles, research is making significant strides toward improving early warning systems, and future advances could provide even more comprehensive protection. AI and machine learning are being used to analyze seismic data more quickly and accurately than ever before, allowing for real-time adjustments to the predicted path of an earthquake. Distributed networks of sensors are being deployed to create a more connected and responsive detection system, with the ability to issue hyper-localized warnings, alerts that could provide specific instructions for a particular building or neighborhood. In the future, as technology improves, these systems could be integrated with smart city infrastructure, offering a fully automated response to earthquakes that goes beyond just issuing alerts, allowing for proactive damage control. In addition to the technology itself, another key factor in the success of early warning systems is public education and preparedness. It's not enough just to have a warning system in place. People need to know how to respond when they receive an alert. In Japan, for example, citizens regularly participate in earthquake drills, which help them learn how to react quickly and calmly when a tremor hits. Awareness campaigns, educational programs in schools, and government initiatives all play a crucial role in ensuring that people are ready to take action when the moment comes. As more regions adopt these technologies and integrate them into their disaster management strategies, the effectiveness of early warning systems will only improve. This shift could be a game-changer for communities living in earthquake-prone areas, providing a much-needed layer of protection that reduces the devastation caused by these unpredictable natural disasters. The road to global implementation is still long, but the potential for saving lives, reducing economic damage, and improving recovery times makes it a priority that could significantly alter the future of earthquake preparedness. As we bring this exploration of megaquakes and their potential impact to a close, it's clear that the threat these natural disasters pose is both immense and multifaceted. From the physical devastation of the ground shaking to the long-term psychological and social effects that ripple through communities, we've seen just how deeply a catastrophic event can alter the course of lives. And while we've covered the science, the technology, and the emergency response strategies that are currently in place, one thing remains clear: the threat of a megaquake is real, and it is one that we must take seriously. However, even in the face of this daunting reality, there is hope. The progress we're making in areas such as seismic early warning systems, infrastructure resilience, and public preparedness shows us that we are not powerless in the face of disaster. Technology is advancing, research is being conducted, and more communities are beginning to recognize the urgency of preparedness. The very fact that we are talking about these topics today shows how much awareness has grown and how much more needs to be done. While the ground beneath us may shake unexpectedly, we are building better ways to weather the storm. We've seen how countries like Japan have embraced early warning systems that are saving lives, and while this technology is still evolving, it holds immense promise. As artificial intelligence and machine learning continue to develop, we're looking at a future where hyper-localized, real-time alerts could become the norm, giving people those critical few seconds, or even minutes, to act. This could make all the difference between life and death, turning what was once a near-impossible disaster into something far more manageable. Yet, for all the technological advances, human preparedness remains the cornerstone of any successful response. Knowing how to respond when disaster strikes, whether it's through participating in drills, understanding the systems in place, or simply knowing how to act in those first critical moments, can make a world of difference. It's about ensuring that individuals, families, and entire communities are ready to act when the worst happens, not just waiting for someone else to step in. But even as we grow more resilient, we must continue to remember that the threat of a megaquake isn't something we can ever truly predict. While we can't control when it will strike or how powerful it will be, we can control our response. Whether it's advocating for better infrastructure, pushing for more widespread implementation of early warning systems, or simply preparing ourselves and our loved ones for the worst, we can take action. And in doing so, we take a significant step toward reducing the destruction and loss that could otherwise follow in the wake of such a massive event. It's a daunting reality to face, but it's also one that calls us to action, to invest in knowledge, invest in technology, and most importantly, invest in people. For when a megaquake does hit, it won't be just about surviving the tremors, but about coming together as communities, working together as nations, and helping each other rebuild. In the end, whether we're talking about the science of seismic activity or the human capacity to endure and recover, one truth stands firm: we are stronger together. And if we can prepare, stay informed, and act decisively when the time comes, we can make sure that the story of a megaquake doesn't end in devastation but in resilience, hope, and recovery. Thank you for joining us on this deep dive into the terrifying possibility of a megaquake and what we can do to prepare for it. We hope this video has provided you with a better understanding of the risks and the steps that are being taken to protect us. If you found this video informative, please like, comment, and subscribe for more content like this. Stay prepared, stay informed, and remember, knowledge is our greatest tool in the face of disaster.